my name is Massimo Rudan. I'm the teacher of the class, and I shall wait for about 10 minutes in order to let more students to connect. By this time, I can see 11 students connected. If you have any problems in hearing or seeing, you may raise your hand. Or you may activate for a second the microphone if you do not succeed otherwise, and speak into the microphone. So we are going to start formally at 5:10. So there will be time for other students to connect. The first hour will be devoted to the presentation, and before the presentation there will be a short description of the material that is already present in the website, so you will be able to check whether the website is visible to the students.
Hello, Professor.
Hello?
I heard that someone is playing piano in your home. Someone is playing the piano in your home, right?
Oh, you refer to the music. It's a background, but it's not a piano, it's a harp.
Okay, thank you.
But it should be soft enough not to disturb the lesson. There will be an intermission every hour. So at the end of hour 1, there will be an intermission of 10 minutes. And then we shall start with hour 2. And when we have 3 hours, like on Tuesdays in the morning, there will be 2 intermissions, one after hour 1 and the other one after hour 2. Okay, we'll be starting in 1 minute. E, okay. So students should access this, and I have set up the website of this class as open to everybody, so everybody can just enter and watch the material. And there is some material that is already loaded. So I will briefly. The first information is entitled Warning about accessing the websites, because there is a website of mine that is the standard traditional website where all the material of my classes is loaded, but that is accessible only from inside the Faculty of Engineering. So in this period where we are, so to speak, secluded because of the pandemics, I can access my office only from time to time. Okay, so I cannot access my standard website every day. But of course I can access this virtuale website at any moment. So the information here simply says all the material that I'm going to produce in this semester will be loaded into the virtuale website. Okay, this one, the last one. As soon as I have access to the other website, I will also duplicate the material into the other website, okay, that is accessible from the faculty only, okay. By the way, the material that was loaded into the standard website before February 2020 is accessible to the students. So if you go to this website here, you'll find it, okay? And you also will be able to see some material, but not the newer or the newest material of this semester. Information number 2. This course is made of 2 modules. One module is, the total is 9 credits. The first module is 3 credits, and the second module, that is also called with this name, Advanced Solid State Sensors, is made of 6 credits. And the second module of 6 credits is also available to students that belong to the Italian program of electronics, the program that is given in Italian, and also to students that belong to the international program in electrical energetic engineering. Okay? So if there are any students that belong to the programs that are different from the international program in electronics, they are not required to attend the first module. They may just decide to attend the second module only. Okay? So the second part of the information in the website describes these aspects, okay? So the second module, whose name is Advanced Solid State Sensors, will start after about 30 hours of lessons, because the 2 modules are delivered in series. Okay? Of course, students may attend also the first module if they like, the students of the other programs, okay? The students of the international program in electronics must attend both modules, okay? If there are students of the other programs who decide to start attending the second module at R31 or from R31 on, in order to be able to know when the second module will start, they may drop me a message roughly around the 5th of October, just to be sure. This is my email address, okay? Of course, you may use this address also for questions. If any of you has questions that are not urgent, they may just drop a message to me and I will answer, okay? And if the question is of general interest to all students, I will answer the next available lesson. The third part of the information, that is entitled General Information for the Students, is the information about how to manage, how to access my standard website, not this one, the standard one, okay? The one that is unreachable for me to upload material from outside the faculty, okay? This is a rather long document, okay? So I'm not going to read it now because it is not urgent, okay? It is just a description about how to reach the website and how the website is organized, okay? You see, it is rather long. And the last part of the information that is present is the presentation of the course that I'm going to start in a minute, okay? But before concluding this description, I just want to add that after the completion of each lesson, I will add material to this website that they are looking at. And number one, the material is a short list of the topics that have been touched during the lesson. And the other one is the audio recording of the lesson. Okay, so when I will start with the technical part of the lesson, I will upload the audio recording of the lesson. Okay, so now I'm going to change.
Sorry, Prof.
Yes.
Where we can find the record of the lesson?
Do you see on the screen the word Argomento 1?
Yes.
Okay, after the lesson is completed, say half an hour or so, because I have to change the format, okay? I will upload the recording. The recording does not exist yet, okay? I do the recording during the lesson. Okay. And then I upload it into this website. It's okay? Okay, so now we go to the official presentation of the class. So I take another file. Okay, so we start with the formal presentation. As I said before, the general name of the course is Semiconductor Devices and Quantum Computing, made of 9 credits, 90 hours. It is made of 2 modules, and the second module is called Advanced Solid State Sensors, made of 6 credits and 6. The 2 modules are given in series. These slides are loaded in the website Virtuale. They are already there. And they will be also loaded as soon as possible in the other website. Okay, so you may write down, if you wish, the address of the other website. But it is anyhow, you find it in the presentation that is already loaded. So I will quickly go through these items. Who are the students to which the course is addressed, some details, schedule, aims, prerequisites, how exams are dealt with, references, contents, contacting the teacher, possible subjects for the thesis, and another thing that has nothing to do with electronics, the solid state electronics, is IEEE. So the course, as I said before, is made of 9 credits. It belongs to the master program in electronics, the one that is given in English. Okay, so the name of the master program is Electronics for Intelligent Systems, Big Data and Internet of Things. And the course belongs to the first year, first semester, first year. Okay. The second module is elective in the second year of the master program in electronics engineering in Italian, and is also elective in the master program in Ingegneria dell'Energia Elettrica, that is power engineering given in English. And in this case, it belongs to the first year, okay? Of course, any other student who is interested may register and attend this course. The initial day of this semester was yesterday, as you know, and the semester will be finished on December 22nd. There are 8 hours that are allocated to this course for a total of 90 hours, okay? So that we have to complete 90 hours. 30 of them belong to the first module and 60 to the second module. The words that are in light gray are not relevant because they refer to the possibility of changing the schedule. However, this course is entirely given in remote connection using the Teams environment, this one, okay? So you should never come to class for this course. 100% of the lessons will be delivered by internet, like we are doing now, okay? So we shall continue until the end of December in this form, okay? I know that there are other courses that are partially given by internet and partially given in presence, but this is not the case for this one. The schedule is visible in the website of the university. Anyhow, we have class every Tuesday from 9 to 12, every Thursday from 5 to 7 p.m. and every Friday from 3:30 to 6:30 p.m. It is not, especially the classes that are the hours that are late in the afternoon, but they had to arrange the schedule to make it compatible with the schedule of other classes that are partially in the building of the faculty and partially by internet. So, you know, it is a difficult period, and we hope that the next semester will improve somehow. I don't think that there will be a need to add more hours, okay, because the hours that are in the schedule are sufficient to achieve 90, and we should not exceed 90 hours in any case. I remind you that there is a national holiday on December 8th, so there will be no class on December 8th because it is a national holiday, so not this one and not any other class will be active on that day. Essentially, this course is divided into 3 parts. In the first part, that coincides with the first module, I'm going to provide the basic physical and mathematical concepts that are necessary to understand the transport phenomena in semiconductors, derive the mathematical model for the solid-state devices, and explain the functioning of the most important solid-state devices. And then we shall continue applying the model to the description of devices, sensors, and memories, different types of sensors and different types of memories. And the final part will provide some basic information about quantum mechanics, not that much, enough to describe some application to quantum computation. That is the final part of the class. So what are the prerequisites? Meaning, what are the topics that students are essentially expected to know already before they start this class, okay? Of course, you should know basic concepts of math and physics, okay? These concepts are assumed to be already possessed by the students because they have acquired them in the bachelor program, okay? And also, students should have some concepts about the electron devices, basic concepts. So very likely you have them already on the bachelor program. This is not enough because we shall improve during this course. So in this course, there will be further and more complex mathematical and physical concepts that will be delivered to the students, okay? These concepts are not elementary because this is a master program, and they will be explained to you. So it is not necessary that you possess these concepts beforehand, okay? But using these concepts cannot be avoided. This is why I have to explain these concepts during the class, okay? Otherwise, if we fail in providing the information about the important mathematical and physical concepts necessary for this class, the class would become something totally descriptive, okay? Just talk, okay? Which is not enough for a master program. The exams are oral. They would be oral even without the pandemics, okay? Exams here are always, in my case, oral. And obviously, in order to take the exam, you should connect yourself to the website, okay, that is shown here. Be aware that the website allows the student to register for an exam even if the administrative condition of the students would forbid the students to take the exam. Why? Because it is assumed that from the time you register to the time you take the exam, you have time enough to fix your administrative position, okay? Remember, the system tells me whether the administrative position of the student is okay. If it is not okay, it's forbidden to me to take the exam with the student, okay? So I just tell the student, please fix your position first and then come back for the exam. And of course, during the pandemic emergency, the exams are carried out by remote connection using the Teams environment. There is a problem with this, that for each student that wants to take the exam, I have to check the connection. Okay, I have to check whether the connection is technically okay for the student to take the exam. So that means that I have to close the list 5 days before the date of the exam. Okay, So if the exam is on the 10th of January, the last day for the student to enter the list is January 5th. Why is it so? Because I need a few days to contact individually each student to get, I have to get the ID of the student to check the identity, and then I have to perform a connection just to check the quality of the connection and provide the student with the instruction for the exam, okay? So the list closes 5 days before the date of the exam. Please remember this. Now I'm going to give you a list of references. Let me put them on the screen. Okay. All these references are made of books. Some of them are like 1.3 and 1.6. They are written in Italian, so they are of little use for most of you, but this list is general. It applies also to the students of the Italian program, okay? And 1.9 is the notes, that is the material that I'm going to load day by day in the Virtuale website, and other material is already present in the other website. So if you now go to the other website after the end of this class, you'll find many slides, many files that will be used later, okay? Also of interest for you are references 1.4 and 1.5. Reference 1.4 that has a title in Italian, but it is written in English, and it is a partial collection of the slides. And 1.5 is a more detailed description of many of the subjects of this class. You should not buy any of these books, okay? These books are available in the faculty library, okay? So if you need to consult, you may simply ask the book from the library, okay? So please consider that these books are just given as references, okay? Of course, every book has some mistakes in it. So in particular, the mistakes that are in book 1.4 will be noted by myself when I show the corresponding page, okay? I will point out if there are any misprints or typos in the slides. Instead, for book 1.5, there is a list of mistakes. This is called errata corrige here, that is posted in the website. Okay, so if you go into the website, you can see the list of mistakes. Of course, during the course, I will use more material than that present in the slides, okay? So all material that is not included in the collection of the slides is already uploaded in the website, or will be uploaded by myself, if it is new material, day by day, at the end or at the beginning of each lesson. Okay? So please check the website. One warning. If you take reference 1.4 from the library, please be aware that the numbering of the pages that you see in the book, in the paper books, is different from the numbering that you can see in my slides on the computer. Because from the date of publication of the paper version of the book to now, I have added more slides. So the page numbering is not consistent. So please do not refer to the page numbering if you take notes. Please refer to the title and content of the page, not to the page number. Okay? The title of this slide is Contacting the Teacher or Tutor. There is no tutor. So consider it as if it is contacting the teacher. As long as we are in the pandemic, there is only way to contact the teacher, that is by email. Unless you ask questions directly during a lesson, okay? So if you do it by email, please drop a message to me at the address that is written here. Okay, so for the moment, there are no other possibilities, not in person, nor by telephone to contact me. It may be too early for a thesis, but I just want to list a number of subjects that may use at a later stage for those who are interested in a thesis in semiconductor devices. Possible subjects are physical models for carrier transport using the Boltzmann transport equation of the Schrödinger equation, or both. Special numerical schemes for the solution of the models. Carbon nanotubes or silicon nanowires. You know that now many advanced devices have a cylindrical form, and if they are made of silicon, they go under the name of silicon nanowires. And if they are empty cylinders, they go under the name made of carbon, they are carbon nanotubes, okay? The subject that is in light gray is impossible now to pursue because it needs a laboratory, and we don't have laboratories. Another possible subject is about advanced memories, like, for instance, phase change memories that are a rather modern type of memory, very powerful, very compact, very important, and they are made of special materials different from silicon that go under the name of chalcogenide materials. All the theses that I have listed are carried out either by myself or by colleagues that work in a research center that belongs to the University of Bologna, that is called Advanced Research Center on Electronic Systems. The short is ARCES in Italian. And probably you already know, or you're going to know, some of these colleagues who are listed here. All of them work in the fields of electronics, and all of them belong to the research center. Research center that is entirely embedded in the University of Bologna. It is not a spin-off, it is not a private company, okay? It's just a part of the University of Bologna as an independent branch. This is just the Italian name of the research center. What is coming next has nothing to do with this class. There is an institute that is called the Institute of Electrical and Electronic Engineers, in short IEEE, that is a technical institute made of technical societies, and there are many technical societies, among them the Society for the Electron Devices, that the one for circuits and systems, quantum electronics, whatever. So why am I giving you this information? The information is that sooner or later we'll start a thesis. You will need access to technical papers. That means having access to technical journals. Members of IEEE, of course, have access to technical journals published by IEEE. That are many, because each technical societies has one or more technical journals, okay? So the reason why I'm giving you this information is that if at any time in your life you may decide to become a member of IEEE, remember that if you do it as a student, you pay much less than as a regular member. So this is not a commercial for IEEE, this is just a useful information for the students. As a student, you pay, I don't know, $25 a year. If you are a regular member, you pay considerably more, okay? Student means bachelor student, master student, but also PhD student. So some of you will continue to have a low registration fee also later on if they become PhD students. So remember this, okay? I can provide this information because for many years I have been the student branch counselor for the University of Bologna. Now the student branch counselor is a colleague. It's Professor Rebecca Montanari of the Department of Computer Science, okay? So this information about IEEE has no relation with the official teaching. It's only meant to inform the students about the existence of a student membership, so a much cheaper form of membership. To conclude, have some other warnings to give you. As I already said before, this class, but also all other classes of a master program, cannot be qualitative. Qualitative description of functioning of devices, processes, whatever, is just a starting point. It must be followed by a complete quantitative analysis, okay? So that means the physical concepts behind it, behind any device or process, must be understood, and the mathematical approach must be possessed by the student at the appropriate level. So my advice is, remember, calculations are not the object of this course. They are just a tool, okay? It's like being able to read music to the purpose of performing a sonata, okay? You must be able to read music rather professionally, okay? And you must learn the mathematical tool also professionally. Never try to learn the mathematical processes by heart, by memory, okay? Because in my experience, this leads to a disaster, okay? If you have problems in understanding, ask questions immediately. Drop me a message. Don't wait too long, okay? Don't try to memorize equations. Try to understand how they come about, how they should be manipulated, and so on. Another information is that, as I said before, on a day-by-day basis, essentially at the end of each class, I will reformat the audio recording of the lessons, and I will upload it into the website. For the moment, in the Virtuale website, because it is immediately accessible to me. Later on, also in the other website. It will be the same material duplicated in the two websites. Okay. So I think this is a good help for the students, because if they failed in taking notes, or if they did not understand something, they can go over to the recording and listen again to the lessons, okay? It is not an encouragement not to come to class, okay? It's just to help the students. Also, as I said before, with no hurry, but it is useful if you read the instructions showing how to reach some of the material that is associated with this course, okay? Because all these instructions are posted in the website, okay? So you'll see there is much material already there, and the rest of the material will be the new one, so to speak, will be uploaded during the lessons. For the moment, refer to this website, okay? So this is it for the presentation. We have a few minutes left before the intermission, so if there are questions, you can send me a message using Teams, or you can just talk. Okay, so I see there are no questions for the moment. Let me check whether there is any question by email. No questions. So for the moment we stop and we shall start again at 6:10. 6:10, okay? Thank you. Okay, so we start again, and I'm going to show the slides. So these slides are taken from reference 1.4. Only the title of each chapter is written in Italian, and also the caption of the slides are in Italian, but all the rest is in English. And the first subject that we are going to consider is that of crystals. In many cases, the material of which the semiconductor devices are made is a crystal. I'm going to rotate the slide. Okay. So if you look at the left part of the slide, you see the scheme of a two-dimensional cross-section of a crystal. A crystal is by definition a periodical arrangement of atoms, so that one atom or a group of atoms repeats itself periodically in the three directions of space. So in the example that you see in the figure, this is no real crystal, it's just an example. You can consider the three atoms that you see, the small one black, the larger one gray, and the other large one dark gray. So they are a group of three atoms, and they are drawn differently because it is assumed that they belong to different species, chemical species, okay? And this group of atoms repeats itself periodically. So each triplet of atoms in this example is repeated, you see, horizontally at equal distances, and also in the vertical direction, also at equal distances. Okay. Obviously, a real crystal has three dimensions, so you must assume that the plane that you see in the figure is repeated also in the third dimension, normal to the screen, okay, normal to the slide. So the group of atoms whose periodic repetition forms the crystal is called base. So in this example, the base is made of three atoms. And the directions in space along which the base is repeated are crystalline directions. Okay, so in the figure, all the horizontal lines are crystalline directions, and also the other lines that are not exactly vertical, okay, are also crystalline directions. So a first property of crystals is that it is not mandatory that the crystalline directions in the crystal are mutually orthogonal. Okay, it may happen that depending on the structure of the crystal, they have angles that are different from 90 degrees. Okay. Of course, the crystalline direction intersect each other. So the intersections are point of the space, and these points are called nodes. Okay, so you have crystalline directions, nodes, and then you have, of course, also crystalline planes. For instance, the plane of the slide is one of the possible crystalline planes over which all these atoms are placed, okay? And also the crystalline planes repeat themselves parallel to each other. In this example, okay, they are not visible because they are parallel to the plane of the slide, okay? Now, it is very convenient to associate geometrical concepts to the physical object that is the crystal. Okay, so when you start with the crystal, you introduce the crystalline directions that are geometrical concepts, of course, the crystalline planes that are also geometrical concepts, the nodes, and so on. Okay, so after you have associated the sufficient that are necessary for describing the crystal, at some point you eliminate the atoms. You say the atoms for the moment are not necessary because I'm going to consider only the geometrical concepts. So at this point we move from the left part of the figure to the right part, in which you can see that we have just the same arrangement of crystalline directions and nodes as before, but we don't have the atoms anymore. Okay. So you see the nodes that are the white dots. They are not atoms. They are just geometrical points in which two crystalline directions intersect each other. And we start with an assumption that is not very realistic, but for the moment it is very convenient. We assume that the crystal is infinite. Is infinite in all directions. Okay, of course, real pieces of matter are not infinite. Okay, but for the moment we consider that the crystal is infinite because only an infinite structure can be really periodic. Okay, if you take a finite piece of matter, it cannot be periodic because when you reach the boundaries, the periodicity is finished. Okay, so for the moment we consider the geometrical structure associated to the crystal as infinite, and then we select arbitrarily a node as origin. Okay, so in this picture the origin is indicated with O, and then we take any other node like the one that is indicated with P. Okay, and then we consider a vector of the space that connects the origin with the other point P. Okay, so this vector OP connects two nodes. So in the language of crystals, any vector that connects two nodes is called translation or translational vector, okay? So OP is an example of a translational vector in 2 dimensions. Of course, you must think that in reality we have 3 dimensions, okay? In the example that you see in the figure, obviously you can think that when you start from point O, you can reach point P by going horizontally along vector A1. So you go horizontally by 2 steps along the direction of vector A1. And then you go upwards along the direction A2 by 3 steps. Eventually you reach point P, okay? So you have intrinsically defined 2 vectors that we call A1 and A2, such that these 2 vectors can be combined in a linear combination in which the coefficients are integers. In fact, you remember we have 2 steps horizontally and 3 steps upwards to reach point P, okay? And you can easily see that any combination of integers using A1 and A2 allows you to reach any node in the plane, okay? The 2 vectors A1, A2 form a basis in the plane. Obviously, in 3 dimensions, you must consider that there will be also another vector that is not written in the figure that we call A3, such that any linear combination of A1, A2, A3 using integer coefficients will be able to describe any translation vector of the crystal, okay? So A1, A2, A3 are called the characteristic vectors of the lattice. In general, the characteristic vectors are not mutually orthogonal. In fact, in this example, they have an angle that is different from 90 degrees. And also, their length is not necessarily equal. You see that A1 is longer than A2, okay? So they play the role of the unit vectors of the standard Cartesian reference, but they are not actually unit vectors. They are not mutually orthogonal and their length is not necessarily equal. By the way, the choice of the characteristic vectors is not unique. Also, the other vectors A1, A2 that are drawn a little bit up to the left would be possible characteristic vectors, okay? So at this point we have a geometrical construction made of nodes, crystalline direction, crystalline planes, translational vectors, and characteristic vectors, okay? So this geometrical construction is called Bravais lattice. Bravais is written in the figure. So this is the Bravais lattice, and the Bravais lattice is also called direct lattice. Okay, it's another name, direct lattice or Bravais lattice. Okay. By the way, A1, A2, A3 also form a basis not only in the case where we are using integer coefficients, okay, but we may think of any linear combination of A1, A2, A3 coefficients, okay? In this case, the general real coefficients, we define any vector of the space. Well, let's define a special subclass of vectors of the space that is the class of the translational vectors, okay? Another important concept that is associated to the lattice is the concept of elementary cell. Now consider the parallelogram here that I'm pointing with the mouse, okay? You can easily see that this parallelogram is centered on this node, okay? So it is uniquely associated to the node. And if I replicate this parallelogram over the whole lattice, I am able to cover completely the lattice, okay? So this parallelogram is a possible example, elementary cell. An elementary cell in 2 dimensions is an area. In 3 dimensions, of course, is a volume that is associated with the one-to-one association to the nodes. And that means that there are as many cells as nodes. And the elementary cell is also such that the union of the elementary cells covers completely the lattice, okay? You may argue that the lattice is infinite. Okay, so you mean you need infinite cells to do so, okay? Of course, you can define the elementary cell also for a finite crystal, okay? We shall see it in a minute. The choice of the elementary cell is not unique. If you go from this one to the other one that I'm pointing with the mouse on the left here, you see that this cell is simply the same parallelogram as before, just shifted, okay? So it is still associated to the node, okay? So this is also a good elementary cell, okay? Now let's take another example, the one that is up left, okay? This is just the same example as before with another little shift to the left, okay? So is this a good elementary cell? In principle, you would say no, because this cell is touching 4 nodes. So it looks like it is not associated with the one-to-one association with the nodes. However, you see that this cell touches 4 nodes, but each node that is a vertex of the cell, is also shared by other cells. So each node belongs actually to 4 cells, okay? So one cell touches 4 nodes, but each node touches 4 cells. So there is still a one-to-one correspondence, because we can think of associating 1/4 of the node to this cell, one other fourth from here, one other fourth from here, and one other fourth from here. So this is also a good elementary cell, okay? Actually, it is very useful because you see that the sides of the cell coincide with the characteristic vectors. So this is a very useful choice for the elementary cell. There is another possibility to construct the elementary cell, and this is shown on the right. Okay, it looks strange, okay, because the boundary is not so regular, but if you look at it, you can see that this portion of the boundary that I'm pointing with the mouse belongs to the axis of the segment that connects the node of the cell to the neighboring node on the right. So you start from the node, you go to the next node, you have a segment, you take the axis of the segment, okay, and a portion of this axis is the boundary of the cell. Then you continue. From the same node, you go to the other node here that is also a neighboring node. In this case, the segment is not drawn, okay, but it does exist. You take the axis, and this is a portion of the axis. Then you go from this node to this other node. This is the segment, this is the axis. Then you go from this one to this one. The axis is the dashed line, but this line is outside the boundary, so you don't consider. Then you go from this node to this. You have the segment, the axis, and then you complete. Okay? So this cell belongs uniquely to the node. And you can apply another property of the axis. You remember the axis of a segment is the locus of the points that are equidistant from the extremes of the segment. Okay, so each point along this thick line has the same distance from this node and this node. And this means that all points that are to the left of the thick line are closer to the center of the cell than to this node. But the same applies to this. All points that are below the thick lines are closer to this node than to this, and so on. So this special cell with the strange construction have an extra property, and the extra property is that all nodes in the interior of the cell are closer to the node of the cell than to any other node. Okay, so this is a special and very important cell, and it is so important that it takes a name. So this cell is called the Wigner-Seitz cell, this one, with the spatial construction. It is the Wigner-Seitz cell. Of course, this is in the plane, okay? Later on, we shall see an example of the Wigner-Seitz cell in 3 dimensions. What happens when we have, instead of having an infinite crystal, what happens when we have a finite crystal? Okay, of course, there will be boundaries of the crystal. So assume that this upper line that I am touching with the mouse is the upper boundary of the crystal. So these other lines on top do not exist, okay? Assume that this line here is the right boundary of the crystal, this is the lower boundary, and this is the left boundary, okay? So it looks like we cannot anymore define the elementary cell, because you see immediately that we can define this cell, but then if you go down and consider this other node is on the boundary. So if we try to draw a cell, we shall get only 1/2 of the cell, okay? However, if you go up, the same applies to this point. We shall have only 1/2 of the cell here, okay? So in the case of a finite crystal, we perform a mathematical trick. It is something that you cannot do in nature, okay? But you can do it mathematically. You can think of folding the crystal on itself. What does it mean? If you fold the crystal in such a way that this node coincides with this, so you fold along the horizontal direction, okay? So this node becomes identical to this. This node becomes identical to this. This node becomes identical to this, and so on, okay? Then the half cell on top will be completed by the other half cell at the bottom. Let me try to give you an example. If this is the plane that you are looking at, okay, you do this. You fold it like this. This is a purely mathematical construction. You fold it like this in one direction, then you fold it again like this. In the other direction, and then, well, with a piece of paper it's over, but you think of folding again in the third direction. It's a mathematical trick that you can actually do. So if you take a finite piece of matter and make it round, substantially you reconstruct infinity, because you can periodically continue forever after the folding, okay? So this folding is a mathematical trick that allows you to restore the full periodicity of the material. So it also allows you to define in full the elementary cells everywhere in the material. Of course, this has consequences, but they are not so severe, so we can use them. Okay. Now let's continue with some little calculations. You remember that we defined the translational vectors. Okay, the translational vectors are linear combinations using integer coefficients of the characteristic vector. So one example is here. M1, M2, M3 are integers. This is a linear combination of the characteristic vectors, and this is a translational vector that we call L. L is a symbol that we shall use for the translational vectors. The other possibility is that instead of using real coefficients, not integer coefficients. So let's call them mu1, mu2, mu3. So this is any general vector R of the space, okay? It can be written as a real combination of the characteristic vectors, okay? Now you remember that at some point we consider a possible elementary cell like this one. So we consider a cell in which the sides coincide with the characteristic vectors in the plane they are A1, A2. You remember from geometry that if you have a parallelogram like this, whose sides are A1, A2, you can calculate the area of this parallelogram by taking the vector product of A1, A2 in module, okay? So you take the module of the vector product of A1, A2 and you obtain the area of this parallelepiped, okay? If you extend this reasoning through 3 dimensions, so if you take an elementary cell such that in 3 dimensions the sides are A1, A2 and A3, okay, you obtain a prism, okay, and you may wish to calculate its volume. So what is the volume of a prism in which one side is A1, the other side is A2, and the other side is A3? You remember from geometry that the volume of such a prism is the mixed product of the 3 vectors. So for instance, you can take the vector product of A2 times A3, which gives you again a vector, and then you take this vector and multiply it scale 1. You obtain the volume of this cell, okay? Of course, the order of A1, A2, A3 must be chosen in such a way as to obtain a positive volume, okay? So this is implied, okay? The volume that you call tau L, because we are in the direct lattice, is by definition positive, okay? You also remember that if you take a mixed product, you can swap the dot indicating the scalar product with the wedge indicating the vector product, okay, and the result does not change. So you can define equally well this volume as A2 dot A3 wedge A1 or A3 dot A1 wedge A2, okay? Obviously, this is the volume of a prism, okay? What happens if we change the form of the elementary cell? Does the volume change? The answer is no. Why? Because all cells are equal to each other, and all cells, regardless of the form, cover completely the volume. So that means that the volume of the elementary cell is an invariant property of the lattice. It does not depend on the form of the cell itself. So once you have calculated tau L, this tau L is the same for every cell. In the special case of a finite crystal, of course, there is another possible method to calculate the volume of the cells. You consider the total volume of the crystal, which is finite in this example. So the total volume of the crystal is omega, okay? And then you divide this volume by the number of the cells. In this case, you find in another way the volume of the elementary cell, okay? The total number of elementary cells of a finite crystal is called NC. Of course, for an infinite crystal, the total number of cells is also infinite, okay? But if the lattice is finite, then the total number of cells is also finite. And you can calculate it in an easy way, because consider this as a finite crystal. Okay. If this is a finite crystal, you count how many sides are there in the first direction, 1, 2, 3, and 4. And then how many in the other direction, 1, 2, 3, and 4. You have a total of 16 elementary cells. This is obvious, okay? So for a three-dimensional lattice, what you do is that you simply count how many sides of the cells are present in the direction number 1, assume they are n1, then in the direction number 2, assume they are n2, and in direction number 3, and they are n3, and then you take the product, and of course this gives you the total number of cells of the lattice, okay? This is not the end, because to the direct lattice we must then associate another lattice that is called reciprocal. So we now must define for a given direct lattice another lattice that is called reciprocal. In order to define the new lattice, we must define the characteristic vectors of the new lattice, and we shall call them B1, B2, B3, okay? The definition is very simple. B1 is given by the vector product of A2 times A3 divided by the volume tau L. B2 is defined as the vector product of A3 times A1, again divided by tau L, and B3 is defined as A1, A2, vector product A2 divided by tau L. It is important to notice two things. One thing is that the indices are always in the same order. You see, B1, the indices are 1, 2, 3. So 1 is followed by 2, 2 is followed by 3. Here we have 2, 3, 1. So 3, 2 is followed by 3, and 3 is followed by 1. And here we have 3, 1, 2. Okay, so this is the first observation. The second observation is that the characteristic vectors A1, A2, A3 of the direct lattice, of course, have the units of length. they are measured in meters or centimeters or whatever, okay? They are lengths because they are the distances between points of space. These vectors B1, B2, B3 are defined as the product of two vectors of the A type divided by the volume that is a product of three vectors of the A type. So two vectors in the numerator and three vectors in the denominator. So B is the inverse of a length. It is measured in meters to the -1 or centimeters to the -1 or whatever. It follows that a product of one vector of type A and another vector of type B is necessarily a pure number because it is a length times the inverse of a length, okay? And we can easily demonstrate that if you take any A vector like A sub I and you take the scalar product with any other B like Bj, the result of this product will be 1 if the indices I and j are equal to each other. Instead, the product will be 0 if the two indices are different. Okay, so you remember we can use a compact notation delta. This is called the Kronecker delta. Okay, delta ij means 1 if the indices are equal to each other. It means 0 if the indices are different. Okay, how is it so? Well, it is easy because if you take A1.B1, okay, and you observe the definition of B1, if you take A1 dot, you repeat the definition of tau L. So then you divide by tau L, you get a 1. If instead you take A2 dot B1, here you have A2 dot A2 wedge a product in which two vectors are equal, and you remember from geometry that in this case the result is a 0. Okay, so this defines the characteristic vectors B1, B2, and B3 of the reciprocal lattice. So it defines completely the reciprocal lattice. Of course, the reciprocal lattice will have crystal direction, crystal planes, nodes, and elementary cells. So we can make a calculation to determine the volume of the elementary cell of the reciprocal lattice. We just use the same definition as before. So the volume of the elementary cell of the reciprocal lattice is B1 dot B2 wedge B3, and this is something that we call tau G, capital G, okay? And after some calculation, if you replace the definitions of B1, B2, B3, you find that tau G is just the inverse of tau L, okay? So the product tau G, tau L is 1, okay? To conclude, we now introduce another lattice. The other lattice is called the reciprocal scaled lattice. Okay, how is it defined? We define the reciprocal scaled lattice by taking the characteristic vectors B1, B2, and B3, and then we multiply them by 2 pi. So we use an auxiliary triplet of vectors that are 2 pi B1, 2 pi B2, 2 pi B3. And we are going to define in this way the so-called reciprocal scaled lattice. In the reciprocal scaled lattice, we have again translational vectors, and these translational vectors, as usual, are linear combinations with integer coefficients. We may call them n1, n2, n3 of 2 pi b1, 2 pi b2, 2 pi b3. So these translational vectors of the reciprocal scale lattice, we call them G. Or we may also consider vectors made of linear combinations with real coefficients, Ni1, Ni2, Ni3, of 2 pi b1, 2 pi b2, 2 pi b3. So these are general vectors of the reciprocal scaled lattice, and we call them K. Obviously, G and K have the units of the inverse of the length, because they are linear combination of quantities that contain B1, B2, and B3. Finally, we must consider the volume of the elementary cell of the reciprocal scaled lattice. But this is very easy, because since we obtain the scaled lattice by multiplying each characteristic vector B by 2 pi, the volume of the elementary cell will be tau capital G, this one, multiplied by 2 pi to the third power, and we call this tau small g. So tau small g is the volume of the elementary cell of the reciprocal scale lattice. To conclude, in the reciprocal scale lattice, we may define, of course, the Wigner and Zeit cell, as we did in the direct lattice. Okay, the Wigner and Zeit cell of the reciprocal scale lattice is very important, and in particular, a very important one is the Wigner and Zeit cell that is centered in the origin. It is so important that it takes a special name. So the special name, it is written here in the page, is the Brillouin zone, or also the first Brillouin zone. The first Brillouin zone is the Wigner and Zeit cell of the reciprocal scale lattice centered in the origin. Centered in the origin. Why is it so important? We shall explain it later, okay? But remember the name. One last comment. Why do we need a reciprocal lattice? Why is just not enough to consider the direct lattice, okay? And why then we shall take the scale lattice in which we multiply by 2 pi all these vectors? The reason is very simple. We are considering periodic structures. When you consider a periodic structure, you expect that the physical properties of the structure will also be periodic. So when you want to describe periodic functions mathematically, it is very convenient to use the Fourier series or the Fourier transform. And you remember very well that the Fourier transform brings one space into another. Probably you are accustomed to the Fourier transform in time. So if you transform with Fourier a function of time, you obtain a function of frequency. And frequency is the inverse of time. Or better, you obtain a function of angular frequency, omega, and omega is 2 pi multiplied by the frequency. In our case, we have periodic functions that are periodic not in time, but in space. So we shall do the Fourier transform in space. And the Fourier transform in space brings the direct space R into the reciprocal scale space K. Okay? We shall come again to this issue in the next lesson because now it is 7. So we stop here for the moment and we shall continue tomorrow afternoon. If there are questions, you may ask them directly by activating the mic.
Sorry, Professor.
Yes.
What mean the 3n that we have discussed about during the calculate of the volume with the number total of the cell? N1, N2, and N3.
What is the meaning of N1, N2, and 3?
Yeah.
They are just arbitrary integers. If you take just a regular vector like k, okay, its components are the projection of k on the axis, and they are real numbers, okay? These axes are not mutually orthogonal, but it doesn't really matter, okay? So you have a system that is not orthogonal. So for the general vectors like k, Ni1, 2, and 3 are the components. For a special vector like G, N1, N2, and 3 are the components because G is a translational vector, so it connects one node to another, okay? So for the moment, N1, N2, and 3 are arbitrary, just integer numbers. Nu1, Nu2, and Nu3 are just arbitrary.
Not this little n, the big one above. When about NC, omega,
NC, capital NC,
yeah,
this one?
Yeah.
NC is the total number of cells of the direct lattice. N1 is the number, remember the example here, if you want to count how many cells are there in this lattice, okay, you count how many sides, 1, 2, 3, 4. This is capital N1. Then you count 1,
yeah, I understand.
3, 4. This is capital N2. And then you go to third dimensions, you get N3. Okay, is it okay?
Yeah.
Okay.
Thank you so much.
No problem. We see each other tomorrow.
See you tomorrow. Have a
Bye.
good evening.